Okay, so today's last lecture on sensors, and we'll move over to interfacing on Thursday. So I just brought some items to summarize what we discussed on sensors. So one interesting thing I just saw yesterday, I showed you this digital dial calipers a couple of weeks ago, and I explained the original ones were truly absolute scales. They were a tellurimeter inductocene. I hope you still remember what a tellurimeter is and what inductocene is, right? So they were truly absolute, and you could power them down, and then you could power them up, and you knew where they were. Then people wanted to save a few cents and switch to capacitive readout, which wasn't a tellurimeter. In other words, it was incremental, not absolute. So what they did, they cheated and kept the thing running, and when this auto power off, it just turned off the display. It didn't turn off the inside counter, so it looked like it's absolute. It wasn't, and the batteries used to die every few months. So strangely enough, I just saw that Mitutoyo came out with supposedly, hold on, I have to select projector. So I just saw in a magazine ad this week that Mitutoyo came out with a new device, supposedly, which is basically exactly what the old devices were. Okay, and what they came out with, what they did, they came out with this new caliber, and they claim in the ad, which you can't see, but I'll read to you. It says true absolute inductive technology, battery life 3 years. And so basically what they did, they went back to the old design, and now they're advertising it as very long battery life. Okay, so basically that's exactly how digital calibers started 20 years ago. They were exactly this design, and now it came back finally because the other design was really bad, because it was just good for the battery makers. Okay. Good. So, and the other advantage I want to remind everybody, in calipers, the inductocene had another big advantage compared to capacitive readout. Even if both were absolute, both were tellurimeter principle based, the inductive in a machine shop had a big advantage over capacitive. And let's say if somebody can remember what it was. Water, yeah, because capacitive is very sensitive to water because the dielectric constant of water is very high. So if any cutting fluid or water or oil gets between the scales of a capacitive device, it will change the reading a lot, make huge errors, while the inductive is totally immune to water. It will read the same if submerged in oil, submerged in water or air. So basically, it started with the right idea. For the last 10 years, nobody made them this way just to save some cents, and now it's going back to the right idea. That is very common. You would think people in industry are smart and they know what they are doing, but it's not so. But I gave you the examples of the encoders, which nobody does full disk averaging, although the principle is known for 200 years. But you can't buy an encoder with full disk averaging, which will improve the accuracy at least 10-fold, if not 100-fold. There's many, many examples of things that everybody knows it's the right design and nobody makes. So it's kind of strange. I can give you many, many examples of designs in industry which are wrong, and everybody knows, and it's easy to see why. I gave you the other example of normalizing, that everybody does a minus b divided by a plus b, while it's much more complicated than holding a plus b constant, right? And nobody does it. At least I've never seen anybody do it. So, and I know it works because I use it myself each time I have to do something like that. So I can give you a long list of examples that just the fact that the whole industry does something, it doesn't mean it's right. Because the process is somebody does something wrong, but it sells well, so everybody copies them, okay? And especially in Asia, they think that we are smarter in design, so something here is wrong, they say it must be right because these people in the States did it, so they copy it and then basically, and once it dominates the market, nobody deviates until somebody starts thinking and says the whole thing is wrong. It's a lot more common than you think. That the product is badly designed and all the competitors is equally badly designed because one is influenced by the other. Okay, so to summarize all what we learned about sensors, so I put together a summary sheet, and there's nothing new in this sheet, but it will be attached to the lecture, so you'll be able to refresh your memory. What makes a good sensor? So the first one is obvious. Second one, differential if possible, because of all the reasons we discussed. Better noise immunity, better stability, better linearity. Remember this issue with the even harmonics cancelling out in differential, better linearity. But if you can't make it differential, at least try to make it with a reference arm or a dummy arm and a measuring arm. And the example I gave you, and that's an important example to remember, that if you wanted to make a strain gauge differential, let's say you have a cantilever beam which is bending, and you wanted to make a strain gauge differential, you will put one resistor here and one resistor here, one will compress, one will stretch, or some idea like this. You can make it truly differential if you want to, okay? But it's more complicated, so what you do it all from one side. But the way they do it from one side, they do it in a way like this, in a bridge configuration. So one resistor is variable with stress and the other is just to match, so the temperature affects both. Physically, if you look at a strain gauge, it looks like this. Actually, they only put these two resistors on the sticker. So if you look at the strain gauge, it has one resistor like this, and then it has one resistor like this, and these can be connected together. So these are so this is stuck on the beam where this is the direction of stress. So this is affected by stress and temperature and corrosion and everything, and this is affected by all the same factors but not by stress, because it can easily flex in this direction. Okay? So that's an example where it's not differential, but it has most of the advantages of differential because it has a compensating or a dummy member. And that is a very common idea. Whenever you can't make it differential, at least try to do it like this. Okay? Now, say if you deal with thermocouples, a thermocouple measures the temperature between 2 points, but the other point cannot be room temperature because room temperature fluctuates and so on, so you make an artificial reference in the thermocouple reader, and it's called an artificial cold junction. So you make a reference which is like this arm, and you compare it to the other. So this idea of a dummy reference or just the internal reference and plus a lot of circuits now add the auto zero, because you have a computer you can do auto zero like DVMs and so on. So this is a close approximation to differential if you can't do it. So that's number 2 and 3. We talked about AC. Okay, we talked many times that for some reason time or frequency, which is the same as time, is 1 over time, can be measured by many orders of magnitude more accurately than anything else. So just to give you an example, if you want something which measures lengths to 1 ppm, you need an interferometer or grating interferometer. Interferometer to 1 ppm costs 50,000 or 100,000 bucks. If you want something to measure time to 1 ppm, you can buy a quartz watch, it costs 10 bucks. So that's the ratio of difficulty of measuring time versus other things. Right? So basically any quantity you would want to measure to 1 ppm, except time, you'll have to pay tens of thousands of dollars. If you wanted a scale which can measure, say, a gram to a microgram or a kilo to a milligram, which is 1 ppm, I don't even know if such scales exist, but there will be tens of thousands. A normal scale would measure a kilogram to maybe 10, 20 or 50 milligram, or measure 100 gram to 1 milligram. But if you wanted a scale which will measure to 1 ppm, absolute, not just resolution, it would be tens of thousands. If you wanted a voltmeter which can measure a volt to a microvolt, it's a very difficult problem. So I went through this many times. So sometimes it's very easy to convert the measured quantity to time or to frequency, and whenever that's possible, you get a big advantage. Okay. Now, okay, massive averaging, we harped on that a lot. tellurimeter principle that, as I mentioned before, I've never been in a class that anybody ever heard of it, but that's one of the best principles there are to make absolute gauges which have very long range, very high resolution, and you can make more complicated tellurimeters, but even the simplest tellurimeter, which uses 2 frequencies, typically gives you 8 digits of resolution. So because I explained before that a phase meter can be made very easily to 1/100th of a degree, and a good phase meter will go to 1/1000th of a degree. Okay, so we are talking about a phase meter which is accurate to 1 part in 360,000. So let's say 1 part in 100,000. So 1 part in 100,000 is 5 digits. Okay? So if you have a 2-frequency tellurimeter, one measures the coarse and one measures the fine. So if you select the frequencies right, you can get 5 digits from the first frequency with the phase meter and 5 digits from the second. So you can get up to 10 digits from just a simple tellurimeter, which is way more than you need, because of course the absolute accuracy can never be that good. But tellurimeters is one of these few instruments which are not expensive and can get you to the 1 ppm level. And if you look at their specs on the internet, there is a nice article called The History of the Tellurimeter, if you Google it. It shows you the performance. For example, the standard tellurimeter today measures 1 kilometer to 1 millimeter, or to 0.5 millimeter. And it's limited not by the internal accuracy, it's limited just by the uncertainty of propagation in air. Because it sends a microwave and the microwave comes back, but the air density changes, the air moisture contents changes, so there is a 0.5 ppm uncertainty about the speed of light or speed of electric wave, which is the same. And that's what gives it the 1 ppm. Internally, it's 0.01 ppm. Okay, so tellurimeter is one of these amazing instruments that can easily get to the 1 per million limit, partially because they're really measuring time. Internally, they're measuring time. That's why it can be made so accurate. Okay. And this rule about what is difficult, what is easy in sensors, that's number 8. So if somebody wants you to make some feedback sensor for a servo and they just need 1%, any way you build it, it will work. You can build it inductive, capacitive, optic, everything will work 1%. If somebody wants it to 0.1%, you have to be a bit more careful. Maybe you need a bit of a lookup table, things like that, okay? But if somebody wants it to 0.001% or 0.001%, none of these normal tricks will help you. Like a lookup table wouldn't help you. The reason a lookup table wouldn't help you because the minute-to-minute change will be more than this. So if unless you calibrate every second, a lookup table wouldn't help you. Because for a lookup table to work, you need stability. Remember lecture number 1, that today you don't need absolute accuracy, today you only need stability. But to get to 1 ppm, you also need long-term stability of 1 ppm, so you can calibrate it. And all these things also don't have the stability of 1 ppm. For example, if you take a block of steel, take a massive block of steel and polish the ends and measure it to be 1 meter, if you come back next year, it's not going to be 1 meter, it's going to move 1 or 2 ppm, just from instability in the steel. I don't know if you know, when they invented INVAR, does everybody here know what INVAR is? Okay, INVAR is a metal with a 0 temperature coefficient. Because the standards used to be made from different metals, platinum and so on, but they all change with temperature, so you have to measure them. So some fellow, very smart fellow in the French Standard Institute worked on this problem and came up with an alloy which doesn't move with temperature, and that's called INVAR. And everybody in the world of metrology got very excited, because now you can make standards that you don't have to worry about the room temperature when you use them. So they switched the international meter and everything to INVAR, and turns out 10 years later that INVAR was very stable with temperature but changed with time by itself. So all the standards were wrong except the British standards that, because of tradition, stuck with bronze. Because, you know, bronze, maybe naval guns, they used it 1,000 years, whatever. So they didn't want to change to any new material, especially not one invented by the French. So because of that, they could recalibrate. All this happened 100 years ago. They could recalibrate based on bronze standards. But later on, they invented super-invar, which is also stable with time. But that's after many, many years of extra work. So even a piece of metal which is carefully machined and polished is not stable with time to 1 ppm, and that change with time is totally unpredictable. It's not that it grows every year, okay? Now, it turns out there is only one book which gives this data about how metals are stable with time, and that book, of course, is out of print, okay? It's a book by Rolt, the same guy who did the optical tellurimeter. The book is called Gauges and Fine Measurements. You don't have to worry about it because it's out of print, okay? But it's the only book that I've seen which gives tables where people actually measured pieces of metal over 100 years, because this takes 100 years of data to know, and wrote down different metals, how they changed over 100 years, okay? Today, not too many people have this patience to do this 100-year research. But what it shows is that the changes were unpredictable. It's not that you could extrapolate anything. The same piece of metal became bigger, then became smaller, then for 20 years didn't change. Okay. It has to do with crystallographic transitions in the metal. Some crystal structures pack better than others. So when you get a slow shift from one crystallographic formation to another, it shifts. So basically, when you get to 1 ppm, you have to think about things you never heard of. Okay, like the crystallographic changes in metal. If you make a voltmeter to 1 ppm, you realize that just connecting the wires to the voltmeter generates a thermoelectric effect, because the wires are different metals than the post, and creates a galvanic effect, because the slightest amount of moisture in the air will form a battery between the wires and the post, which will also give you a 1 ppm error. Okay, and there's 10 other effects you never heard of. Okay, so I'm just trying to explain the amazing difficulty of getting something to work to 1 ppm unless it's time or frequency. Okay? And I should add another rule here, which I mentioned at the very first lecture. If somebody asks you to design a servo system, the time allocation should be 80% the actuator, 70-80%, 10% the sensor, and 10% the software. Most inexperienced designers do it the other way. They do 10% actuator, 10% sensor, and 80% the software, and then they realize it will never work. Because then they realize all this phase shift and instability problems, and they throw it all out and start again. Okay, so don't even start the project to write the code before you spend 80% of your allowed time in the actuator. Okay. Unless you can find it off the shelf and it's perfect, but if you have to design it, that's the order of difficulty in a servo system. Okay, and with this we end the session on sensors. What I wanted to do is two more things. If you have any questions in general about sensors, not even following the lectures, but any general question about sensors, it's a good time to ask them. And if you don't, I want to talk to you about some exotic sensors, which are very interesting. And I want to give you two examples, which are very, very interesting, because both appear like problems that there is no way to sense. Okay? Both examples are actually from military and spying. A lot of sensors, very clever sensors, were designed for intelligence work and spying. So if you want, I would say the smartest sensors you've ever seen were designed for spy work. Because first there was a huge incentive. And no budget limit, a huge incentive. And there is amazing ideas. Maybe I should describe three sensors, two designed for spying and one designed for military, because they're all very unusual sensors. So the first one of them, I think most of you know of. If people are talking in a room and you have no way to get to that room to bug it, put a mic or bug it, You can look at the room from a distance, but there is no way to come close to that room. Okay? How could you eavesdrop on what these people are talking? Today, maybe there's other tricks. Today you can, without them knowing, activate the microphone in the smartphone. So that's the way it's done today, right? I'm serious. That's what the Stax virus was. Okay, so today it's done by taking over the computer without them knowing and activating the microphone. That's the standard way. Okay, but let's say they're smart enough not to turn on the devices. So how would you pick up a conversation in a room that you can't come close to? So I'll give you a hint. This was invented many years ago by a very clever Russian who was also the inventor of this electronic musical instrument. I forget what it's called, where you move your hands and it senses a capacitor and plays music. The same clever Russian. Okay? His name escaped for a moment. So is anybody here, I thought you would know about that, because that's a very famous story. Does anybody know about how the Russians did it? And now everybody can do it. Okay, so this Russian, because he was a musician, he figured out that if you speak in a room, the windows will vibrate a little bit from the sound waves. Not much, but on the other hand, in a telephone, when you look at the diaphragm of a telephone microphone, you also don't see it vibrate. The diaphragm of a microphone and a telephone only moves nanometers. Like you have a crystal mic, like most mics are today, or you have a electromagnetic mic. If you measure how much actually the mic moves from the sound waves, it's nanometers. So if you speak in a window, in a room, the windows will actually move from the sound waves nanometers. But the way a window moves, if a window is sitting in a frame, the way the window moves, it can't move in and out because it's anchored to the frame, so it will move this way, it will bow in and out. Okay? So now if you take a laser and you shine it at this window, when the laser will come back, because the window bows in and out, the laser will come back more or less collimated. You can also do it in a slightly different way. You can shine the laser here and then the angle will change. But the main thing will change is if you illuminate the window with the laser, when the light comes back, the collimation will change. Okay? So if you put a small detector here, smaller than the beam, if the collimation changes, that signal will change. So these are the sound waves. They cause the window to deflect. So if you look at the output here, you'll get something, some voltage, which represents the curvature of the window. So the window acts as a mirror, as a spherical mirror, which changes the focus. Okay? So basically, this will represent the curvature of the window, and the curvature of the window is actually correlated to the sound waves hitting. Now that window moves maybe less than a micron, but it doesn't take much, because if you do a calculation, if you are 100 meters away, okay, and this moves a micron, this will move like centimeters. This is a simple calculation. Take say 1 meter, move it by 1 micron, so that's 1 ppm. Okay? Now if you're 100 meters away, shining a laser at this window, and this angle will move 100 ppm, okay, 100 ppm of, 1 ppm. 1 ppm of 100 meters, okay, is 100 micron, right? Because a ppm of a meter is a micron. ppm is 100 micron. So 100 micron, well, at 100 meters it would be centimeters, but 100 micron is enough. 100 micron, if you put a small detector here, 100 micron movement is a tenth of a millimeter. It's enough to modulate the light. Okay? You certainly do other tricks to optically magnify it, but even if you are across the street shining a laser at a window, the light coming back will move. It will be a tenth of a millimeter based on what it said. So you can pick up the sound from a kilometer. That's by aiming a laser pointer at the window. Okay, so that's a classic, that's a well-known story. You can even buy these things. That's a very old idea. It fooled the Americans a long time. There are two things in the US embassy in Russia was built, and the US was able to build it. And then, of course, the KGB infiltrated the construction team, and they installed a couple of very, very dangerous bugs that didn't have any wires and couldn't be detected. Okay, and these bugs were there for many years until they were detected. So another bug, besides this, what the Russians also did, they gave a gift to the embassy of an American eagle. So it's an American eagle made of brass. So there was a big eagle, and there was a wooden frame, and the eagle was mounted like this, and behind it was another piece of metal, the background. But there was no wires, no batteries. So the Americans inspected everything given to the embassy 100 times. They took it apart, it was just a brass eagle, no batteries, no wires. But it turns out it was a microwave, because you have a plate here and you have a plate here, and this is a microwave resonant cavity. So when you spoke in the room, that vibrated, so that distance changes by a micron. Now if you beam microwave at it, and it comes back, and if you beam microwave at the resonant frequency of this cavity, and the cavity will move even by a micron, the resonance will change. So you look at the amplitude of the return on the waveform, you can hear everything said in the room. And that was in the American embassy for 10 years, before somebody noticed there's microwave beamed at the embassy, and tried to understand why, and figured it out. So everything said in the American embassy for 10 years was transmitted directly to the KGB. So these are very clever sensors. Okay. Traditionally, people would put bugs, okay, to eavesdrop. Intelligence agencies would put bugs in the walls, okay, or bugs, phones in the walls, and these bugs would transmit. You know, bug is a term for a listening device, okay? Not like bug in software. So. Traditionally, people would put listening devices, hide them in the wall, okay? And then these listening devices would transmit. But then it was very easy to find them, because all what you had to do is you come into the room with some receiver which has a very wide bandwidth. Imagine a spectrum analyzer. A spectrum analyzer is something which displays this frequency versus amplitude. So when you look, you put a spectrum analyzer in this room, you see some standard spectral lines. You see something at around 1 megahertz, and that's what? AM stations. Then you see something around 100 megahertz, FM stations, TV. You see something at a gigahertz, and that's what? Smartphones. Okay, it's full of 90 because of all of you guys with the smartphones. Okay, so basically that's what the spectrum looks like. You see some other bands, standard bands, 450 megahertz CB, 27 megahertz CB radio. So that's what the spectrum looks like. So if you brought a spectrum analyzer in this room and became very quiet and looked at it, and then you started talking, if there was a bug in this room which transmits, you looked at the spectrum, you started talking, suddenly a spectral line will show up when you talk. Okay? Or something will change when you talk, so you know there is something transmitting when you talk. Okay, so this is very easy to find, so it was considered a very primitive idea, a very primitive bug. But when electronics got more sophisticated, people started doing clever things. They made bugs which store. They have a digital storage. They store everything said for a whole day, and then in the middle of the night, they transmit everything very fast in 1 second on a high bandwidth. But even if you were there in the middle of the night, something will bleep. You don't know that because it's not caused by your talking. It's just a timer. So in the middle of the night, you will see suddenly this, which is a day's worth of talking transmitted at a much higher bandwidth, so it only takes a second. Because remember, talking is only 3 kilohertz. If you transmit it at 3 megahertz, it's compressed in time, 1,000 to 1, right? If you transmit it at 30 megahertz bandwidth, it's compressed 10,000 to 1, so a days of talking could be transmitted in a few seconds. So once digital electronics came up, people did that, and it was assumed that this is undetectable. A, because it only comes up, maybe comes up once a week for a few seconds. B, when it comes up, you don't trigger it. So when you look at the spectrum, many things come up and disappear. Like somebody turns on his cell phone and shuts it off. So many things come and go, and it doesn't mean it's in this room. You don't know where it is, right? So for a while, this was considered undetectable. So the spy agencies included a lot of the, installed a lot of these things, feeling pretty safe that these will be undetectable bugs. But very quickly, somebody figured out how to detect any bug in a room, even if it's powered off, even if you never turned it on. If you just planted an electronic device in the room, somebody figured a very, very easy way to find out that something electronic was planted in the room. Now that sounds like a completely impossible thing, because how would you detect something which is not even turned on? So basically what I'm claiming is that there is some magic thing that you go into a room and tells you are there electronic devices in the room or not. So if you take out your computers, you take out everything, it will still say there is some electronic device left, and it will tell you where. Because when you scan, it will beep every place there is an electronic device. So this looks like a really impossible sensing problem. It's supposed to discriminate between electronic devices and non-electronic devices. For example, if there's an electrical motor, it wouldn't beep. But only electronic devices, even if they are not powered, even if they have no batteries, even if they are shut off, even if they are broken. Okay? So even if you hide a transistor in the wall, or an IC in the wall, it will find it even if it's not connected to anything. So most people, when they think about it, say that is not possible, and that's why it gave a false sense of security to the people who installed the bugs. But it turned out that somebody figured out how to do it, and all these bugs were found and of course misused. Because once they were found, they weren't taken out, but the wrong things were said, so they pick it up, right? So once you know it's there and the people who planted it didn't know you found it, it's very bad for the people who planted it. So I'll give you a hint. I know that you wouldn't be able to figure it out because, it's a very difficult problem to do. The solution is trivial, but it's not so easy to think of it. But I'll give you a hint. All electronic devices somewhere have diodes. They have something non-linear, right? Because if you have a transistor inside, a transistor, even when it's powered off, behaves like two diodes, right? If you take a transistor, if you don't use it to amplify, it behaves like I should draw it this way. Say, this is a NPN transistor. And a PNP transistor would behave like two opposite diodes. A FET device would behave like diodes. So basically, every semiconductor device parts of it will behave as diodes. Now if you have a relay, if you have an electric motor, you have an electric oven, it doesn't behave as diodes. It just behaves as resistors or inductors. So all electrical devices, if you don't know what it is, somebody gives you a box and you have some wires coming out and they ask you what is it. If you measure that box and in all directions it behaves as resistors or capacitors or inductors, you can say that's some electric device. I don't know what's inside, but it's not electronic. It doesn't have junctions or transistors. Now if you take the same box and you measure it with an ohm meter one way and the other way, and the resistance is different, you measure one way and the other way, the resistance is different, you say there must be some diode inside. Otherwise, if you have a black box, and you have some wires coming out of it, and you take an ohm meter and measure this way, and then you take and reverse. This is plus minus, and you reverse and you get a different reading. There must be something nonlinear inside. Is that clear to everybody? Because if you take a resistor and you flip the leads, it will read the same. If you take a diode and you flip the leads, in one way it will conduct easier than the other, and that means it's not linear. Okay? So if you have a black box if it had a resistor or capacitors or inductors or anything except semiconductor devices, any outputs, if you reverse the leads from plus to minus, it will read the same. But if you had one diode somewhere and you reverse the leads, it will read different. Okay? So that's a hint. The difference between electronic devices and non-electronic devices, that electronic devices have to have something nonlinear, and this is a side effect. This is not what makes them electronic, but electronic devices use junctions, and as a side effect of using junctions, something is not linear inside them. They were not intended to be nonlinear. It's just a side effect of having to use p-n junctions or any kind of junctions. Okay, so now that you know the hint, how would you make a sensor which will sense electronic devices? It doesn't have to be for spying. Imagine you have a conveyor and you have to sort out junk, say recycle garbage. So you have a conveyor and you have on the conveyor a dead fish and a tin can and then some electronic discarded iPhone. And you have to have in the conveyor a robot which pulls out all the electronic devices. So it's the same problem, it doesn't have to be for spying. So now you know the hint that the dead fish and the tin can will not have anything nonlinear inside. But the electronic device will have somewhere nonlinear junctions inside. So how would you, without connecting wires to it, how would you know that? So I'll give you a minute to think, because that's really an interesting idea. Yes, there is some idea at the end.
Magnetic fields and
So I would use induced magnetic field, and then how would I know?
You alternate it. You alternate it. You can alternate magnetic field and you look at the difference.
Okay, so I alternate the magnetic field. If there is a DC magnetic field, it wouldn't do anything, right? The DC magnetic field, any piece of steel in the wall will have much more effect. But I can use an AC magnetic field. But then it's alternating already. So how would I know? If I move an AC magnetic field, it will respond much more to some rebar in the concrete than to a junction.
If it wasn't symmetric, if your output wasn't symmetric.
You're getting very close. Okay, good. Okay, let's keep developing it. One problem is the magnetic field. If you have a permanent magnet buried in the wall and you measure the overall field, the permanent magnet in the wall will make it non-symmetric too. But still, you are on the right track.
A different kind of wave?
Pardon?
A different kind of wave? Like radio wave?
Which wave?
Radio wave?
You're getting even closer. It's warmer. Okay, so you use radio waves, but how would you detect that there's something not symmetric inside the wall? Okay, so I'll tell you how it's, yes?
do like a positive and negative RF excitation and then pick up.
But RF excitation is this. There is no positive and negative. RF changes from positive to negative 1,000,000 times a second. There is no positive and negative RF. And then what?
Look for response, like a wave response.
You're getting even warmer, but what will you see on the response?
We see different decay constants.
But when you pulse RF, it looks like this. So it only has one decay constant, because the RF is made of positive and negative cycles. Pardon?
Phase.
What's that?
The phase.
It wouldn't really do that. It's not so simple. Also remember, the thing in the wall is very small. You wouldn't be able to see it here. Okay, so the answer is this. If every RF wave, every electromagnetic wave that you send, some of it is reflected. Okay, you can do it several ways, but the easiest way to explain it, if I send an RF wave, say a high frequency RF at the wall, some will be reflected just like light is reflected. So if I have a wall, the wall has some pieces of metal, some pipes, and some black box with a diode inside. And if I'm sending an RF wave to the wall, each object will reflect a little bit. I'll get many reflections from the wall, from the devices inside. All these reflections will be scrambled together, of course, because the RF wave cannot resolve the items. So what I'll get back is like a reflected wave, but the reflected wave will be the superposition of every little object in the wall, including every little pebble. So I'll get a whole bunch of things adding together to the reflected wave, okay? But all of them will be perfect replica of the incoming wave, except the phase, but one of them will be a bit distorted, okay? Because this is nonlinear, so because of that, say it shorts out the positive part of the reflective wave on this in a kind of a highly magnified scale. Instead of looking like this, it will actually look like this. That is highly exaggerated. The actual difference would be 1 ppm, because this thing is very tiny. So the difference would be less than a ppm, maybe part in a billion. So it's certainly not detectable with a scope or anything. But if you take a wave, a perfectly symmetric wave, and you distort it by a very, very minimal amount, maybe a part in a billion. Remember, we're talking here about so many things reflecting and one little diode hidden. It couldn't be more than 1 in a billion difference, okay? But how can I detect that a sine wave was deformed by 1 part in a billion? It's certainly not visibly. Yeah.
Your frequency response, your spectrum.
Ah, very good. Getting warmer and warmer. Okay. So all what you have to do is put up a filter which is exactly double the frequency. So if this was F, if you excite it at F, you put up a narrowband filter at 2F, because any asymmetry, if this was the original spectrum, this was F, if I clip the sine wave, even by a part per billion, it will create a second harmonic, because it's non-symmetric, right? Remember, if it was symmetric distortion, it will create the third, the fifth, the seventh harmonic, just from the Fourier transform. But if it's non-symmetric like this, it will create also second, fourth, and so on. And the biggest harmonic here will be the second, because it's non-symmetric. So the biggest harmonic, if you look at the spectrum, will be 2F, and then it will be teeny 3F, then be a teeny 4F. But the biggest one after the fundamental will be 2F. So if I put a very narrow filter, which only has maybe a bandwidth of 1 hertz, because that frequency I'm sending can be deadly accurate. The frequency I'm sending can come from a quartz crystal. And I mentioned before that frequency and time are one of those things you can measure to parts per billion. So it's not a big problem to get a crystal or a frequency source which is accurate to a part in 10 million, 100 million, even a billion. You can always lock it to some cesium clock or something. So let's say if I'm transmitting here 100 megahertz, I can be sure that the frequency is no more than a hertz off. So I put a deadly accurate filter which is tuned to 2F, and it has a very narrow bandwidth. Now, because it has a very narrow bandwidth, it picks up very little noise, because all the noise in the air is so much nanowatts per hertz, right? If the filter is narrow, it picks up less noise. So if I take a filter at a very high frequency and very narrow, it picks up very little noise. But the moment there is any distortion in the return sine wave, even at parts per billion, that filter will suddenly get a signal. So all what I'm doing is I'm looking at the second harmonic of what I'm transmitting while I'm scanning. And each time there's an electronic device, I'll get a beep from the second harmonic. Now, is that clear to everybody how it works? Okay? Because that principle can be used not just for spying. That principle is a very good principle for a lot of sensitive sensors. Okay, now, just to convince you that that's true, that you can detect a part per billion, think of a regular radio receiver, like in the old-fashioned, like the car radio. I don't know the exact specs on a cell phone today, but even a cell phone will have the same specs. So if you take an old-fashioned car radio, it could transmit, like those things taxis used to have in the cabs. Okay, this thing would transmit 30 watts when it was on. A cell phone transmits 100 times less, maybe 0.3 watt when it's on. And a car radio, typical car radio, will have a sensitivity, which means a signal it needs to receive a call of about 0.3 microvolt. For some reason they didn't measure it in watts. They measured sensitivity in microvolts, but it was on a 50 ohm impedance. For some reason car radios, including cell phones, the output is measured in power and the input is measured in microvolts. It's just a convention. Now 0.3 microvolts over 30 ohm, the power this is equal to is 0.3 squared times 10 to minus 12 divided by 50, right? Because it's V squared over R, and that's in microvolts, okay? So this will be in round numbers 10 to minus 13 divided by 50. So in very, very round numbers, it will be, if this was 100, it will be about 10 to minus 15 watt. So an old-fashioned car phone, in order to receive a conversation, only needed 10 to minus 15 watt. I suspect a smartphone today would be 10 to minus 14, 10 to minus 13. It's a bit less sensitive than a car phone. But it's certainly much more sensitive than 10 to minus 12 watts. Okay? Now, so the ratio of the transmitted power out to the received power in on a radio, in a car radio, is about 30 watt divided by 10 to minus 15 watt. Okay, so again, in very, very round numbers, let's make it 10 to the 16th. Now that's an amazing number. Okay? Think of it. The difference between the signal it transmits and the signal it receives is 10 to minus 16. So here it means that if this distortion gives you a second harmonic, which is 10 to minus 16 smaller, you'll detect it. Okay? There is no other way to detect it. There's no way to look at the, it's no way to look at the appearance. There's no way to look at the phase, because 10 to minus 16, that is such a small change. There's no way to detect it any other way. I shouldn't say no way. I just showed an example of some things that looked like there was no way to do and there is a way. so I shouldn't say there's no way, but it will be very difficult, okay? So if you look even at a cell phone, a cell phone transmits 100 times less and receives about the same, maybe a bit worse. So the 10 to minus 16 will become 10 to minus 14. Let's even 10 to minus 12. So even within your standard smartphone, there is something which can pick up a signal 10 to minus 12 of the signal it transmits. So if you took your cell phone, so your cell phone is tuned to two frequencies, one transmits, one receives. But if you took your cell phone and changed the filter inside, so you transmit frequency F and you tune your cell phone to receive 2F. Okay? Which is very simple to do. It's actually simpler to do than what's done in a cell phone today. Because today the cell phone transmits at F and receives at a frequency which is very little different, F plus delta F. And the difference between the transmit and receive in a cell phone today is small, which makes it much harder. Okay? But so it's much easier to make a cell phone which transmits at F and receives at 2F. So such a cell phone, whenever you walk around a wall, will beep. Whenever there is anything electronic hidden, even if the signal is only distorted by 10 to minus 12, 10 to minus 13. So it'll pick up any electronic device, active or passive. So that's a nice example of something which looks like it's no way to do it, and you can actually modify your cell phone to do it. And you can, before cell phones, all what they did is just had an oscillator, and next to the oscillator they had a filter, a 2F, and just converted this to a beep. When this appeared, it beeped. Okay, is it clear to everybody how this thing worked or works? That's still today. When you call a company to find bugs, you know, the more sophisticated ones, that's what they do. I mean, the military, not private. Private, they probably do use a spectrum analyzer. But when the NSA wants to know if something is bugged, that's what they do. Okay, is there anybody here who has any questions about how this works? Because the principle is a very clever principle, actually. Good. Okay, let's show you even a more difficult problem, which again has a very trivial solution, but most people, when they look at the problem, they say there is no way to sense that. So the more difficult problem, again, and this is taken from military work, also sometimes spy work. In the military, there is ultimate importance, and also in spy work, there is ultimate importance to know if somebody is looking at you. Okay, because in the spy work, if somebody is looking at you, maybe somebody is following you. Now maybe he's following you from a car, and maybe he's following you from a great distance. But if somebody looks at you all the time, it's a bad sign. Okay, somebody is tracking you. Now, in the military, if somebody is looking at you more than 2-3 seconds, it's a very bad sign. Because that means that he is a sniper, and the next second you'll be dead. Right? Because in the military, you know, people don't track each other and follow them. I'm talking in a war. You know, if somebody really looks at you more than 2 seconds, you're dead. Okay, because he's going to shoot you. Okay, so it's very, very important to know that somebody is looking at you, not just passing along like this, but actually staring at you. Because I'm serious, if somebody in a war zone is staring at you more than 2 seconds, then you're dead. Okay, because he has a reason to look at you. He's probably aiming at you. Now, and this problem is compounded because sometimes it's nighttime. So you can say at daytime, maybe you can scan, maybe you can look, but somebody could be looking at you at nighttime with passive gear, not with infrared that you can detect, but with passive gear. Passive gear meaning he can just look at you with binoculars, or he can have a starlight intensifier. There are some binoculars which intensifies, I don't know if you know these things. There's some image intensifiers, which looks like binoculars, but you look at nighttime, it looks like daytime. Because they intensify the starlight until you have full brightness. These are commercial devices. You can buy them, they cost $1,000, $2,000. Okay, so basically, so the question is this: can you detect quickly means within 1 or 2 seconds, that somebody is looking at you day or night, even in total darkness, from distances up to 1 kilometer? Because if it's more than 1 kilometer, you're less worried. Right? He can't hit you. Okay? But certainly you're worried if it's 100 meters. Okay? So again, you pose this problem to engineers, they say, how can I know? It's completely passive. The person looking at you is just hiding behind a bush, nothing active, he's not radiating any energy. So how can I know he's looking at me and not just looking around? And you don't want false alarms, because if he just looks at faces, it will buzz all the time. Right? You just want to know if somebody is staring at you, not just looking around. So, any ideas?
Including if they're wearing something, some vision?
Yeah, most of them have binoculars. The people are the most dangerous who are looking at you through a telescope, because most likely they're looking at you through a gun sight. So that's the worst kind. Okay? So any kind of vision enhancing thing makes it worse. It means they have some good reason to look at you and see well. Okay?
Well, I guess this wouldn't work with the,
Sorry, can you use what?
I guess it wouldn't work with the vision enhancing thing, but could you use the retro reflectivity of their eyes?
Beautiful. That's how it's done. Okay, so I'll repeat the answer. The answer was, just so the mic picks it up, the answer was, can you use the fact that eyes, not just of humans, eyes of any animal are retroreflectors? The answer is yes. Because when we talked about retroreflectors, that's a very good piece of thinking. When when we talked about retroreflectors, we said that if you look at a sphere, and the sphere is made of glass or a material similar to glass, which means index about 1.5, we did the calculation that this light will actually focus at the other side of the sphere. And if you remember, I just repeat the calculation. If this was radius r, and the index of glass is 1.5, okay, and other materials like the eye, it's not 1.5, but it's similar. It's 1.4, 1.5. It's all in this range, okay, because pure water is already over 1.3. Right? So if you just have water, it's 1.3, and you add some gel, whatever, it gets 1.4. So let's say 1.5. And I mentioned to you there is a formula called Lensmaker's formula, which I tried to derive last time, but now I remember. And the formula says 1 over f equals n minus 1. And this is 1 over r1 plus 1 over r2. But here we only have 1 r, so we can ignore this. So this is Lensmaker's formula. So if we plug in the numbers, this is a formula used historically by lens makers to calculate what radius they need to make the lens. That's why it's called Lensmaker's formula. So if we plug in the numbers, we get 1 over f equals 1.5 minus 1, which is n minus 1, divided by r. So we get 1 over f equals 1 over 2r, because that's half over r. So f equals 2r. So it means when we have a curvature of radius r, and a beam of light hits it, and the index is around 1.5, the beam of light will come to a focus at 2r. But 2r is exactly the diameter. Okay, so if you have a sphere or a human eye, if you hit light, it'll come to a focus here, which is a retina, but some of the light is reflected. So the light which is reflected will come back collimated. Okay? So any eye will act as a retroreflector, and I mentioned that's why when you drive and there is an animal on the road, when it's caught in the headlights, the eyes are very bright, and somebody here even mentioned that's why the red eye effect when you take pictures occurs. Because when you take a picture with a flash, the light hits the retina is red because of blood vessels. So what comes back is not just regular light, but red light. And that's the red eye you see on photos. Okay, so if you have a scanner, if you have a laser beam, imagine a laser pointer which is rotated quickly, has to be rotated in 2D. Let's say you have a laser pointer which scans a raster scan. This scene. So the scene is random. So each time the laser beam will hit a random scene, the light will be scattered. Very little light will come back. But if that laser pointer hits a retroreflector, you'll get a bright flash coming back, just like when you drive behind a bicycle rider and when the headlights of the car hits the reflective strip, you get a bright flash. So all that you have to do is put here a partially reflective mirror. Okay? These mirrors are typically half transmitting, half reflecting, just like an interferometer. So now when you have a detector here, okay, you have a detector here, so when this scans a scene, each time it hits an eye, you'll get a spike here. Okay? Now, if the person has binoculars, it actually gets a much better signal. Because when you hit an eye, the aperture of the eye is very small, so only the light which hits the aperture can get in. But if you have binoculars, what the binoculars do actually, they increase the effective aperture, because that's exactly the purpose of binoculars. Okay, now you're picking up this much energy instead of this much energy, so you get a huge signal back. Okay? And on top of it, you can actually, if you scan, you get a double pulse because of two eyes. Okay? So the angular separation, if you scan the scene, you typically get a double pulse, okay, and the angular separation will get down and down with distance, because when a person is farther away, the angular separation will be less between the two eyes. But if he has binoculars, you'll get a small separation but a big signal because of the binoculars, okay? So not only will you be able to say somebody is looking at you, you'll be able to say if somebody is looking at you with binoculars, with eyes, or with a monocular. But basically, if this persists, if you scan the scene, say, and the scan is done very fast, like a supermarket scan, and you scan it again a second later, 2 seconds later, and you still get the spike, because then somebody is staring at you. If you just get it once, maybe somebody just turned around and you just caught him when he was turning. But if the spike comes back next second, he's focused on you. Yes, please.
Wouldn't this be really noticeable to whoever's spying on you?
Pardon?
Wouldn't the scanning be noticeable to whoever's spying on you?
Why?
Because you're shining a laser into their eyes?
Oh no, the laser can be visible. You wouldn't do a visible laser.
Right, okay, so
yeah,
laser.
of course. Yeah, you take a 830 nanometer laser, so you don't see anything.
And that's still well within the 1.5?
Okay, that's why you'll take 830, because if you look at the transparency of an eye, if you took a 2 micron laser, which is even less visible, the eye wouldn't transmit it, and the index would be different. But if you take 830 nanometer, it's invisible, the eye is still fully transparent to it, and the index about the same. It has to be near enough the visible so the optics of the eye will still work, but can easily be 100 nanometer off the end of the visible and you wouldn't see a thing.
So just
Right.
barely infrared?
Pardon?
Barely
Yeah,
infrared.
yeah. Typically, you have to be careful because human vision, they always say, is 400 to 700, okay? But if you do a test, it looks like this, right? It peaks at green, peaks at 500, but it doesn't go to 0 at 700. It just after 700, it still has a long tail. So if you have a very bright source at 750, you still see it. It just looks dim red. Even if you have a very bright source at 800, you still see very dim red. So, but at 830, a source which is less than a few milliwatts, you see nothing. Don't try it because it's dangerous. Because no, when you look at these laser diodes, they look very dim, so you're tempted to look inside, but you'll blind yourself. Because it's like a 50 watt 830 nanometer diode looks like barely dimly red, and if you turn it, it'll blind you. But you only need a milliwatt. So you use a laser pointer at 830 nanometer, which is maybe 10 milliwatt. Okay, and signal is enough coming back. Okay, because again, it only looks at one direction, and you have an optical filter here, which only looks at 830 nanometer and all this stuff. So it turns out if you do a thing like this, with 2 scans, you can tell A, that somebody is staring at you, B, is he using a binocular or not, and C, that he's actually staring for a second or two, and not just moving his head and you manage to catch him. So that's quite amazing, indeed, that you can do that, yes.
Do you have to wear that, like, on you?
Yes. Yes, but it's worth it. It's one. And also it could be, depends, if it's a vehicle, it can be mounted on the vehicle, because, but if you want to, this device is small enough that you can wear it on you. And this is not commercially available, but known to be available. I mean, this is available to the military for 20 years. Different packages, so no, you can't see it advertised, you can never see a picture of it, because it's still classified, but it leaked out. The principle leaked out, and it also leaked out that all armies use it, but you'll never be able to see a data sheet or a picture of it, right? How it looks on the head. But it's small enough, you could wear it on you, on your helmet or something. Any other questions? Somebody else had a question, I think, here.
I was going to ask, like,
Yeah.
if it had a name, but it's classified.
No. It's people call it. It doesn't even have a name. But let me see if I have. If you want to find it on Google, say what you would call it. I'm not even sure. I'm sure if you type into Google looking at you detector. No, I'm serious. This will come up because this is a well-known device. This has been leaked out for at least 10 years or more. So it's not that WikiLeaks or something. It's for 10 years people knew this existed. They knew the armies use it, but if you weren't in the army, in this job where you need one, you never saw one. Yes, please.
Someone's looking at you through a telescope.
Yeah.
What would the signature look like? And is there anything that could be confused with that signature? Like, could it be mistaken for something else?
No, telescope is even a much better signature because telescope has a bigger aperture than the pupil. So as I said, the signal you get back is huge because telescope is like a much better retroreflector and it collimates it better and everything is better. So if you just look with the eyes, you get a little spike. If you look with the telescope, you get a huge spike. And also you can do a range finding at the same time, and because the same laser can also be pulsed and be a rangefinder. Remember, if this laser is pulsed or if this laser is modulated, say this is a laser, and if you modulate it, the same laser can be a tellurimeter. So when you get this reflection back, you can know the distance to the person within a millimeter. So if you know that, you know which power telescope is using. Right? I'm serious, because if you know the distance and you know the signature, you know which power telescope he's using. And I'm pretty sure, I'm guessing, the new devices probably have a readout and saying he has a Kalashnikov Model 7 with a number 6 telescope on it, right? Because it will know the distance and the power of the telescope from that.
Also, how sensitive is the alignment of the telescope? Like, if he's looking just a little bit off, is it your
That's the beauty of it, because if the device sees his retina, he's looking right at you. If he's looking, you can even check, does he see red? Not with 830, but you can do some tricks with somehow to try to deduce. In principle, you can see his retina here. So if this was a CCD, and that's a pure speculation. I know this exists, but the rest is pure speculation. But I'm saying in theory, that if he's looking a bit off, there is no strong reflection. Strong reflection is from the retina, but in theory, when you are really aligned, you see his retina here. So in theory, one can have a camera and looking, is that a picture of a retina of a man or is just a cat staring at you, right? So you can do much more refined things today. But to do the basic things, all that you needed is a laser. Before the laser, there wasn't enough signal to noise to do it. So because of that, laser was invented in 1960. By 1980 and 1990, these devices existed. Today you can do a lot more with the cameras, with analysis, with everything. But the principle was known for at least 20 years and used in armies. Yes, please.
Would it work if there was a camera looking, for instance?
Yes. But in military, that's a bad sign too. Because if a camera is targeted to look at you and keeps targeted at you, in other words, if you move and the camera is still looking at you, that's as bad as a person looking at you, right? That means something is really targeted on you. So I wasn't joking. Yeah. So I wasn't joking when I said that if you detect that signal for more than 2 seconds, you're dead. Because why would anybody in a war target at you and not do anything? In spying, they could be targeted at you and tracking you for years. But in the military, after 2 seconds, if they are really heavy on their sides, you're dead. Yeah. So the short answer is, if this beeps, just duck. Okay, and yes, you have a question.
It's possible there's like glass or other reflector.
No. Okay, that's an interesting thing because the glass will have to be perfectly aligned. So let's say you have a piece of glass here. You have like just a piece of shattered glass which is perfectly aligned, just randomly perfectly aligned to retroflect. But if you move 1 meter, the signal goes away because it's not tracking you. Okay? Because the glass, if you moved a little bit, it wouldn't be perfectly aligned anymore. Remember, we have a beam which is a few millimeters. In order to come back from 100 meters, the thing has to be aligned to a few arc seconds. Okay, so if it's glass and you move this much, there will be no signal. But if it's an eye, the eye will track you, the signal will follow you. So you can tell the difference between a random reflection, like a piece of glass, and something actively tracking you. Because could also be a person here who just looks in your direction but doesn't look at you. You know, somebody looks at the sunset and you're just in his way, okay, and you get a reflection, but when you move, it doesn't track you. So that actually detects by moving. It detects that somebody is staring at you, not just looking in your direction. Yes?
So do they usually have just one beam coming out, or does that beam like rotate to see different?
No, it has to rotate because you don't know what the person is. So that beam has to do a raster scan. Okay, so that beam has to do this, like go like this and raster scan. But that is the same, this device with the beam with the raster scan, you are using every week. You know where you're using it? Where are you using every week a laser pointer with a raster scan? Do you do your own shopping? So how do you check out at the supermarket? You put a barcode. How does a machine know where the barcode is? It has a laser with a raster scan. Actually, it has a raster scan in a special way. It has this kind of raster scan. It has a special scan. So basically, a little laser pointer mounted in a box which does a raster scan in 1 second, you can buy from any supermarket supply. Right? You don't have to develop. Because that's exactly what a barcode reader is. Because when you put the barcode, the scanner doesn't know where you put it and doesn't know which orientation you put it. Okay? So the barcode scanner is a laser pointer and a special mirror. It has a special rotating mirror on a motor. I don't know if you ever looked inside the supermarket reader. I know it says do not look, but it's only 1 milliwatt. You can look diagonally. So inside it has a wheel, and the wheel has mirrors at different angles mounted on it. And the laser hits the wheel, and the wheel rotates. So the laser coming back, and it's not doing a simple raster scan, because that's not very good if the barcode happens to be aligned that way. So because you don't know how the barcode is aligned, it has to do a raster scan in some very convoluted way that it covers all angles. So by putting each mirror at a different angle and rotating, it does a raster scan which rotates. So this whole thing is this big, and they're cheap. And that's all what you need. You need a supermarket unit, you change the laser and put a detector. And then you know if somebody is looking at you. Okay, so it's very simple. Okay, because a supermarket scanner is also 25 years old. It's not new technology. And it only takes 1 second because of this clever arrangement of the mirrors. It only takes less than a second to do a full scan, a full 2D scan. Because you can slide something across the supermarket counter, fraction of a second, it's scanned. Right? So you know that this whole thing is very easy to do. Yes, please.
Do you have a feel for how quickly the signal would drop off? For example, if you have your detector mounted on your head and then looking at your feet?
Say it again, how would the signal drop off?
Based on, I guess, where exactly the eyes are looking. Because you can say, okay, well...
Yeah, I can tell you. These things are easy to calculate. And if you want the calculation, I can do it for you. It's very simple. Because what you do is... Okay, it's a simple trade-off between area you want to monitor, area of you, and signal to noise. Because if you put a super collimated beam, and assuming the eye is super collimated, it will be very directional sensitive. But it wouldn't be good, because not everybody's eye is a perfect retroreflector. I mean, it's just randomly that the eye turned out to be like this, right? It's nothing to do with vision. So you can't really rely on being collimated, and somebody may need glasses, somebody may have bad vision. He can still see you, but he's not perfect vision, so not perfect vision means his retina is here or here. And because of that, you can't really rely on collimation. Okay? So because of that, you have to assume that the beam arrives perfectly collimated, but you have to assume that the beam comes back because it's not a perfect record reflector. So at 100 meters, the beam which comes back covers all of you. So if he's looking at your head or your feet, it'll be the same signal, because if you do a rough calculation, the beam will come back with a few milliradian error, because it really needs a perfect retroreflector to do better. Now, if this is, say, a 10 milliradian error, that at 100 meters, this will be like a meter. So it doesn't really matter if it's looking here or here or here, because the return beam is quite broad. Okay, but the signal, of course, is weak, because you're sending out a beam which enters the eye. Only about 1 to 4% comes back. The reason is surface reflection. We talked about it last time. I didn't get into it, but when you hit something which is not a mirror, there's different reflections, and basically you don't get back much. Okay? Because the retina is optimized to absorb light, not to reflect it, to be sensitive. So you only get back 1 to 4%, maybe even less than that. Then you spread it. Let's say your detector is 1 centimeter, and it comes back 1 meter. So the signal drops 10 to the 4, because it goes by area, right? So this area, 1 centimeter circle, is 10 to the 4 less than that, okay? So you get 10 to minus 2, which is reflection loss, times 10 to minus 4, which is collimation loss, okay? So it's the most what you can get back at 100 meters. At 100 meters, the most you can back is the most is 10 to minus 6 of what you send. And I suspect you more get like 10 to minus 9, okay? But that's plenty. That's plenty. If you're sending 10 milliwatt, 10 to minus 6, you're getting back 10 nanowatt. 10 nanowatt is a huge signal in optics, right? Because considering the bandwidth here is not very high, 10 nanowatt is fine, okay? So that the calculations are very easy to do. So I just showed you how to do them, but you can plug in the real numbers and see. So that's in that order. Okay, so time is up. So I will give you I will post an assignment on the website, on the Connect, okay? But you'll have plenty of time. The assignment is simple. You'll have plenty of time. You'll have at least 2 weeks to do it. It's about 1 hour work, so don't panic. So this week I'll post the assignment. It'll probably be due after spring break, so you have lots of time.